Picture yourself standing on the bridge of a container ship in the North Atlantic. The sun has disappeared hours ago, and what surrounds you now is something that challenges every instinct your body possesses. Waves the height of 10-story buildings rise and fall in a rhythm that seems almost alive, almost personal. Your vessel, a structure of steel weighing nearly 200,000 tons, is being lifted and dropped by water with such force that the entire superstructure groans. Around you, alarms are sounding. Crew members are bracing themselves against railings, and somewhere far below, in the depths of the engine room, engineers are making constant, minute adjustments to keep this floating city from doing something that seems, in this moment, entirely inevitable. They are keeping it from tipping over. This is one of the most remarkable engineering puzzles in the world, not because it is invisible, not because it happens at scales we cannot comprehend, but because it works at all. Because every single day, ships traverse oceans in conditions that should, by rights, turn them into metal coffins. Yet somehow, they arrive. The cargo reaches its destination, the crew returns home, and very few people ever wonder how. The question seems simple enough when you first ask it. How does something so massive, something so utterly dependent on floating on water, manage to stay upright when the water itself is trying to destroy it? But the moment you actually think about it, really think about it, the question becomes almost troubling. A wave that reaches 60 feet in height, and these waves are not uncommon in a storm. That wave contains an almost incomprehensible amount of energy. It can strike a ship not from one direction, but from many at once. It can hit the side of the vessel with a force equivalent to a fully loaded freight train moving at highway speed. How does anything survive that? The answer is not magic. It is not luck, though luck certainly plays its role in maritime safety. The answer is something far more interesting. It is an ancient principle that naval architects have been refining for centuries, a principle so fundamental that once you understand it, you realize it governs not just the safety of ships, but the very nature of how anything floats at all. But before we explore that principle, we need to understand what we are actually fighting against. Most people, when they imagine a ship sinking, picture something dramatic, a vessel that tips sideways, that rolls over like a toy in a bathtub, perhaps taking on water through gaping holes in its hull. This can happen, but it is not the most common way a modern ship finds itself in mortal danger. Instead, what engineers fear most is something far more subtle and far more deadly. They fear capsize. Capsize means the ship has rolled too far over, the point at which a vessel can no longer right itself. Imagine balancing a pencil on its point. You can tilt it slightly and it will fall back to center. But tilt it past a certain angle, and gravity takes over entirely. The pencil cannot recover. For a ship, this angle is called the angle of vanishing stability, and it is the single most important number that exists in naval architecture. Here is where common sense begins to break down. Because when you look at a ship, at its massive hull and its enormous weight, you would think it would be almost impossible to tip over. The thing is so heavy, so broad, so fundamentally designed to sit flat in the water. Surely all of that weight would keep it upright. But that is not the full story. That is not even close to the full story. The moment a wave strikes the side of a ship with tremendous force, the ship begins to roll. The hull tilts. The starboard side of the vessel rises out of the water, and the port side dips deeper in. The weight of the ship tries to bring it back to level, but if the wave is large enough, if the force is great enough, that single roll can continue past vertical. The ship can roll beyond the point where its own weight can save it. And when that happens, when the ship reaches that angle of vanishing stability, nothing can bring it back. It rolls, and it keeps rolling, and within minutes, a ship that was moments before a functioning vessel becomes a grave. This is the nightmare that never leaves naval architects. And so everything about a modern ship, from the moment the design phase begins, is focused on one objective: preventing that angle of vanishing stability from ever being reached. The first and most ancient tool in this arsenal is something so simple that it seems almost obvious once you know about it: the ballast system. Deep inside the hull of a ship, below the cargo hold, below the engines, there exists a series of tanks. In these tanks, water can be pumped or released. During calm weather, some of these tanks might be empty. But as conditions deteriorate, as the ship enters rough seas, officers on the bridge monitor wind speeds, wave heights, and the vessel's own movements. And they make a decision. They order the ballast tanks to be filled. This accomplishes something that is almost counterintuitive. They are making the ship heavier. They are adding weight, often many tons of weight, at the lowest possible point in the vessel. And this extra weight, positioned as low as possible in the hull, does something remarkable. It lowers the center of gravity of the entire ship. A lower center of gravity means that when a wave strikes and the ship begins to roll, gravity's restoring force is stronger. The ship has more power to right itself. Think of it like this. Imagine two figures, both made of exactly the same material, both the same overall size. But one is shaped like a bowling pin, heavy at the bottom and light at the top. The other is shaped like an inverted cone, light at the bottom and heavy at the top. Now push them both sideways. The bowling pin will snap back upright almost instantly. The inverted cone will roll over completely. The only difference is where the weight is distributed. The only difference is the center of gravity. But that is just the beginning. The ballast system is ancient technology, understood by wooden shipbuilders centuries ago. Modern ships face modern challenges, and modern challenges require modern solutions. Here is where it gets interesting. The second critical system is something called the anti-roll tank, or the active stabilization system. In the very heart of many modern ships, there exists a tank that is partially filled with water, but remains sealed from the ocean. This tank is divided by a special partition that creates a U-shaped channel. As the ship rolls, this water inside the tank is forced to move through the channel. By controlling how quickly this water can flow, and by timing that flow with the ship's motion, engineers can create a force that actively resists the roll. It is as though the ship itself is working against the waves, fighting them with water it is carrying inside itself. Imagine you are swinging on a swing set. If someone pushes you at the wrong moment, the push is wasted. But if they push you at precisely the right moment, at the moment you reach the peak of your swing, that push adds to your momentum. The anti-roll tank works on the opposite principle. It creates an artificial drag that opposes the motion. By releasing water to flow through the channel at exactly the right moment in the ship's roll cycle, it can reduce the amplitude of the motion by up to 50%. This is not a small thing. Reducing the roll by 50% can be the difference between survival and disaster. But engineers do not stop there. They have gone much, much further. Some of the most advanced container ships in operation today use something called active fins. These are not biological fins, though they work on a similar principle. They are hydraulic structures that extend from the sides of the hull, underwater, during rough weather. These fins actively change their angle of attack in response to the ship's motion. Sensors throughout the vessel constantly measure the rate of roll, the acceleration, the angle of heel. Computers process this information in real time and send commands to the fins. Adjust left, adjust right, increase angle, decrease angle. All of this happening dozens of times per second. The result is a stabilizing force that can reduce rolling motion by as much as 70%. But you might be wondering, if these systems are so effective, why do ships still sink in storms? Why do we still hear reports of vessels lost at sea? Here is where we must confront something uncomfortable. Because sometimes the systems work perfectly. The crew makes all the right decisions. The engineering is flawless, and the ship still goes down. This happens not because the technology fails, but because it is being asked to do something beyond the boundaries of physics itself. A truly extreme storm, a storm in which waves exceed 70 feet in height, in which the wind speed reaches hurricane force, in which the sea state becomes absolutely chaotic. That storm creates conditions that no amount of engineering can fully overcome. The human mind struggles to grasp the forces involved. A single massive wave striking a container ship at just the wrong angle can deliver a shock load equivalent to the weight of several thousand cars landing on the side of the hull. Add to that another wave striking from a different direction mere seconds later, and you have a cumulative effect that pushes the vessel far beyond the angle where even the most sophisticated stabilization systems can help. In December of 1998, a container ship called the Bremen encountered a storm in the Atlantic that generated waves exceeding 60 feet. The ship rolled to an angle of 60 degrees. Inside the vessel, every unsecured object crashed from one side to the other. Containers stacked on the deck began to slide, but the ship did not sink. It righted itself. It limped back to port. The crew survived because of the systems we have discussed, yes, but also because the Bremen had been designed with something else in mind, the concept of sufficient stability margin. This is where the full brilliance of modern naval architecture reveals itself. Ships are not designed to barely survive the worst storm they might encounter. They are designed with stability margins that exceed what even extreme weather can impose. The angle of vanishing stability is deliberately engineered to be as large as possible. The placement of weight is optimized not just for one condition, but for a spectrum of conditions. The ballast distribution is managed not just for maximum stability, but for optimal stability across dozens of different loading configurations. A ship leaving port with a full cargo of heavy machinery requires different ballast distribution than the same ship in ballast, empty except for fuel and supplies. Modern ships also employ something that would have seemed like science fiction just decades ago. They have sophisticated computer systems that continuously model the ship's behavior in real time. Accelerometers and gyroscopes throughout the vessel feed constant data about the ship's motion. This data is processed by algorithms that predict not just the ship's current state, but its immediate future state. If the prediction shows that a dangerous motion is about to occur, the system can act before the motion becomes critical. The fins can adjust, the ballast can shift, engines can change power and direction. All of this can happen in the space of seconds, driven by pure mathematics and sensors. And yet, despite all of this, despite the anti-roll tanks and the active fins and the computer systems and the ballast management, the most fundamental principle remains exactly what it was when the first sailing ships crossed oceans. It is a principle called metacentric height. This is a measure of how far the center of buoyancy is positioned from the center of gravity. A large metacentric height means a ship will resist rolling and will return strongly to the upright position when disturbed. A small metacentric height means a ship will be sluggish, that it will roll more easily and recover more slowly. The simplest way to understand this is to return to the bowling pin analogy. The weight at the bottom creates stability. The wider the base, the more stable the structure becomes. For ships, the width of the base is, quite literally, the width of the hull. The position of the center of gravity is determined by how weight is distributed. Naval architects spend months, sometimes years, optimizing the relationship between these factors. Every single ton of cargo is positioned with this in mind. Where does it go in the hold? How does its position affect the ship's center of gravity? How does it affect the metacentric height? These questions drive decisions about how a ship is loaded, how it is ballasted, how it will behave in rough seas. The modern container ship represents the culmination of more than 1,000 years of accumulated maritime knowledge. Every component, from the shape of the bow to the position of the engine room to the design of the bridge itself, has been informed by this single obsession, keeping the ship upright in the worst conditions nature can produce. The hull shape has been refined through countless iterations in computer simulations, tested in large wave basins where mechanical wave makers can generate waves of almost any conceivable shape and size. Engineers stand in control rooms watching scale models of ships endure waves that would dwarf real buildings, and they take notes, and they refine designs, and they test again. Some of the most advanced ships in operation today can predict with remarkable accuracy what will happen in a given sea state. They know, with certainty measured in degrees, how much they will roll. They know how long it will take to recover. They know their limits, and they operate within margins that would seem impossibly conservative to anyone unfamiliar with the ocean's power. Captains understand that no system is perfect. No technology is infallible. The sea remains even now a force that demands respect. When a ship successfully navigates a severe storm, when it emerges on the other side with its crew intact and its cargo secured, that is not a victory of one technology. It is not the triumph of computers or sophisticated fins or advanced ballast systems, though all of these play their part. It is the result of knowledge accumulated across centuries, refined through mathematics, and tested against nature itself. It is the proof that human ingenuity, applied thoughtfully and with respect for forces far greater than ourselves, can achieve the seemingly impossible. We can make something float. We can make it carry weight. We can make it travel across oceans. And we can make it survive, even in the most extreme moments when those oceans rise up and try to destroy it. And that, ultimately, is why ships do not sink when they cross the world. Not because they are unsinkable. Nothing is unsinkable. But because the people who design them understand the principles that govern stability, and they have built those principles into every aspect of the vessel's design. The ship does not stay upright through luck. It stays upright because the engineers have eliminated luck entirely, replacing it with mathematics, with physics, and with respect for the sea.